What up, dudes? Here's what we got. You're pushing down on this block at an angle theta, and you have a coefficient of friction mu s, and you want to figure out what is the force necessary, I think it was. Let me read the problem. What is the force? Find the force necessary to start the crate moving as a function of theta, given the coefficient of friction between the crate and the floor is mu s. Okay, cool. So, here's what I got. Let's do some of the forces in the x direction. And if this thing had no friction, if this thing were made out of ice, how would it tend to move?
In the right direction.
To the right direction. So the coefficient or the friction is actually pushing to the left. Okay? That's the first question I ask myself when I want to figure out what the direction that the friction is going to be pushing. What other forces do I see on here? I didn't label them all, or we should. So what other forces do you see?
Normal force and weight.
Good. The normal force, the W. I'm happy with that. Okay. Now, what I'm going to do is I'm going to add the forces in the x direction. Is there any acceleration in the x direction?
Yeah.
Yeah, that's a tricky one. The answer is no. Because remember, it's statically friction right now, and this is right before it starts to move.
What force so you're trying to find the force necessary to start it moving?
Yes,
but it's not moving.
Yes, it's not moving, and I want to break that bond to get it to start moving.
So, are you trying to find that, like, isn't it called the max static friction? Where right before it turns into kinetic friction?
There's a point at which, in fact, I should have done this as a lab. In fact, I did this test using some of the sensors. Next time we meet up, I'll use the sensor and I'll show you guys this thing because I think it's really cool. But if I were to map out the force, it would be like the force would increase and increase and increase, and then it would break, and then there would be like this some point like that. So yeah, it would go up, and then there's a point where, I mean, if you think about it, like, you ever try moving a big desk across the floor?
Yeah.
Yeah, you're pushing on it, and then finally it goes pop, and then it starts going. So anyway, that's what we're trying to find. All right. I'm going to call this F. Let's get all the forces in the x direction. What forces do you see?
So F cosine theta?
F cosine theta, yeah.
Fs.
Minus Fs equals 0.
Yeah.
So F cosine theta equals Fs. So F cosine theta equals mu times my normal force. Got it?
Yeah.
Okay. Do I know my normal force right off the bat?
Yeah, because it's just the weight of the mass.
No, it's not actually. In this particular case, it's not.
Because you have something you have part of the force is acting in the y direction, so the normal force has to counteract that. So the normal force is actually W plus F sine theta.
There we go. If you look at the picture, usually we don't have that force contributing to that normal force, but the normal force has to account for both this W and the extra that you're pushing down at. Does that make sense?
Yeah.
Okay. Now, what I'm going to do is I'm going to solve for F. So I have F cosine theta equals mu W plus mu F sine theta. Okay. F cosine theta minus mu sine theta equals mu W. We good? I do a few steps in my head at the time, and then I pause and wait for you. All right.
Yeah.
So F is equal to mu W divided by cosine theta minus mu sine theta. Okay. So then you just plug in those numbers, whatever those numbers are. Did they give us a number for mu? Find the force necessary to push the crate, given that this thing.
They just give you an angle.
Huh. I wonder why they give you an angle but not the coefficient of mu or w. The reason why I'm wondering that is because if they give you an angle, there's no point in giving us an angle if they don't give us these numbers. I'm hoping that this is correct. They also gave us a check, right? Part B. What does part B ask me? It's saying if mu is equal to 1 over tangent theta, then what happens? Okay, fine. Let's try that.
Well, I think maybe for part A, they're telling you to use information in figure 618.
Oh, I see. Okay.
And in that figure, it's
yeah, there's
the weight
numbers.
is, or
There's
the
numbers.
mass is 32 kilograms.
Yeah. All right, then we can plug in the numbers and we'll be happy. What I'm interested in is what were they saying about mu? If mu equals 1 over tangent theta, then this thing becomes impossible? Well, let's see. Mu equals 1 over tangent theta, then F is equal to 1 over tan theta W divided by cosine theta minus 1 over tan theta sine theta. We cool?
Yeah.
One over tan theta is the same as cosine theta over sine theta. Right?
Yeah.
This sine theta will cancel out with that sine theta, and on the bottom I have cosine theta minus cosine theta. It doesn't matter what the top is, because on the bottom I have cosine theta minus sine theta, which is 0. I'm dividing by 0. So my force is undefined. Interesting. It's saying that if my coefficient of friction is bigger than 1 over the tangent of the angle, I'll never be able to move this thing. I have to think about it, to be honest with you. I mean, that's what the math is telling me. And my favorite thing about this whole thing, about physics, is when the math tells me something, I really got to think about it. I got to sit there and be like, how does that make sense? But apparently it will. It will make sense. It's got to make sense. It's got to come together like that. I'm just thinking, why is that physically true? And to be honest with you, my answer is right now, I don't know. I mean, I'm looking at this, the units work out on this thing. So I don't know why it's true that if the mu were 1 over tan theta, then it'd be impossible to push. Let's try this. What's okay, wait. Yeah, I guess that's just kind of one of those funky things. That's interesting.
Maybe it's like,
Well, the coefficient of friction is so big that it's impossible to push no matter how much you push on it. That's what it's saying. Which is crazy to me.
well, it's probably just the way the angles interact. It's an impossible.
I think you're right. I think that if theta were 90 degrees, right? If theta were 90 degrees, then you'd be pushing straight down on it. That would skyrocket the normal force, which would make the static force bigger. But also, if theta were 90, it wouldn't be moving in the horizontal direction at all. So if theta were really big, like a big number, I'm sure that we could see it if we graph it out. And sometimes what I like doing is I like choosing a number for mu and choosing a number for w, and then graphing this, or you know, like plugging this into my graphing calculator, where I'll have like f equals x times 32 over the cosine of 21 minus x sine of 21. So I just plug in some numbers for this thing, and then I look at the graph and I see, well, how does that trend go and why is it looking like that? Anyway, that's all super advanced analysis. I don't even think that they do that in college, or at least in an undergraduate level college, so hope that helps.
Yeah, it definitely does.